Good morning everyone, my name is Jimmy. I'm a technical support engineer in Diana. So today I'm going to introduce a tutorial called cooling pipe in early age concrete in a two-dimensional heat flow model. So in this tutorial I will explain to you how to do a 2D heat flow simulation in Diana considering cooling pipes. So this is the geometry of this tutorial. So for example, you have this a U-shape concrete tunnel, and for the simplicity, we simulate half of the concrete structure because of the symmetry nature of that is centered around mirror at this plane. So we will simulate only half of this concrete structure, and inside this concrete structure, there are three sets of cooling pipe circuits going through the concrete structure. And there's circus 1 is going in here and out here, circus 2 is going in here and out here, and the circuit 3 is in the bottom of the concrete wall. So say that the fluid is flowing in for example, the longitudinal direction and flowing out of the longitudinal direction as well. And if you want to simulate, for example, the temperature variation at the slice of this concrete structure, you can make use of the Diana 2D generalized plane strain model, and also take into account of the concrete the cooling pipe fluid inflow and outflow as well. So in this case, there are a couple of things to think about. The first thing is to create a geometry of this model, and the second thing is to assign the material properties for the concrete and also for the cooling pipes. And the third thing to consider is the boundary condition of your model. So in this case, there are a couple of boundary conditions it needs to be taken into account. The first is the environmental temperature. So you will have a convection boundary condition between the concrete structure and the air, and you will have a initial temperature you need to assign for the structure, and you need to also assign the material properties for the convection boundary condition, which is the external temperature of the air. And then there is a necessary to consider a heat of hydration. For example, you have this wall is casted on top of the the slab, and upon removing of the framework, and there's a process of heat of hydration, and there will be increasing of the temperature from the hydration. And there's also a cooling effect of the cooling pipes. So in order to simulate this, you need to do a transient heat flow analysis. Then you can simulate the temperature variation in the time domain. So next in the result, we will show you that how for example, the degree of reaction of this concrete changes with the time, and also how the temperature changes inside the concrete as well as the cooling pipe. And you can see that with Diana, you can, without simulating the whole 3D structure, you can also simulate a slice of this structure using the generalized plane strain model, and that will save you a lot of time if you consider the model is relatively homogeneous in the longitudinal direction. So without further ado, let's go into the tutorial. So first thing to do is to create a new project. We call this project Cooling 2D, and we need to activate heat flow analysis, and we will change the dimension to generalized plane strain. With generalized plane strain model, we allowed out of plane shear stresses. So this is a better approximation than the plane strain if there is out of plane displacement that you expected from this sort of model. And in this case, we will input the model thickness to 20 meter and the model size 100 meter, and we keep the rest unchanged. After the project is set, the new project is made, the first thing is to change the model. So in this case, we follow the tutorial. We change the time to day and change the temperature to Celsius, You can also adjust it based on the data you have. So first thing is to create the slab, the concrete slab, and we do it by creating polygon sheet with entering 6 point of the polygon sheet and with the coordinates. And on top of this concrete slab, we build a concrete wall. We create another polygon sheet entering the 4 points, and then we rename this as wall. And because we cannot select the outer edge of the slab because they are overlapping, so next thing to do is to imprint these two objects so that we can select the edges of the slab that is exposed to the air for a boundary condition setting. So next thing is to create a cooling pipe. So in Diana, in 2D model, the cooling pipe is implemented through points in geometry, and after geometry is created, and when you generate mesh, Diana will automatically generate 2D finite elements for this cooling pipe. So we input the position of this first point. So to create the other points for the cooling pipes, I will copy paste the Python script provided in the Diana folder for the sake of time. So I just copy here, paste here, and you can see all the points are created. And the next thing to do is to create a cooling pipe. So what we do is that we go to the geometry and then we create a new cooling pipe set, and we drag the first 4 points to the cooling pipes 1, and we do the same for cooling pipes 2 and 3. And now we have the cooling pipes set up ready. The next thing to do is to assign the material properties. So first we will select the wall, and we select the element class generalized plane strain, and we will need to create a new material, and we call this wall, concrete wall. And we select the class concrete and masonry, and in this case for simplicity we use linear elastic isotropic material, and we also need to enable the heat flow option so that we can input the heat of hydration and also the heat flow parameters. So we first set up the linear material properties based on the tutorial, Young's modulus, Poisson ratio, and also the density. And then we need to enter the heat flow parameters, conductivity and capacity. And because this wall is casted recently, so we need to activate the heat of hydration, and we select this method, pre-processing from the adiabatic heat development, and we need to enter the adiabatic heat development data from the tutorial, and we can copy from an Excel sheet, and you can see the curve here. It goes from 0 at the 0 day at 20 Celsius to 65 degree in the end. And we will also need to adjust the other parameters. We click close, and now the materials is created, and the next thing to do is to apply. And we also do the same for the slab, but here we need to create a new material because the slab is considered casted in the previous stage. So we make a new material with the similar material properties, and we need to activate the heat flow as well, and we fill in the Young's modulus, Poisson ratio, and density. And for the heat flow, because we are not simulating heat of hydration, we only need to fill in the conductivity and also the capacity of this material. Then we apply. And the next thing to do is to set up the cooling pipe properties, and we right click cooling pipe properties. Here we need to set up initial fluid temperature, which is the temperature at the inflow of this cooling pipe circuit. We set it 10 Celsius degree, and we need to make a new material properties for the cooling pipe in order to provide, for example, conductivity and the flux into the cooling pipe. We name it cooling pipe, and we need to enter the heat transfer coefficient, also the product of discharge and heat. We can also enter the time at which cooling starts and stop. So in this case, we by default assume that it is start in the beginning, so we don't have to enter anything. And we will also need to make a new geometry for the cooling pipe to enter the pipe parameters. And this is a 0.084 meter. As you can see that there are 4 points in the cooling pipe. So in order to define the flow direction of the cooling pipe, you need to set it here. So you can order it with this option. You can also do it manually. So you just move the inflow at the beginning of this box, and the outflow from the bottom of the box, and the flow direction will go through this order that you set from 1 to 4 3 in this case for the circuit in the bottom. And we click update, and it will apply. And we do the same for cooling pipe too. We give the initial temperature, material, and geometry that we already defined before. And in this case, because it is arranged in vertical direction, we can just use the menu here to automatically arrange the flow order from bottom to top. And you can check it here from all the way from bottom to top. We update, and we do the same with the cooling pipe 3. We set the same material property, and then rearrange the flow order based on the location of this point. After the material property is done, the next thing is to set up the boundary condition. So first we will set up a convection boundary conditions to account for the convection between the concrete structure and the surrounding environment. So we need to select all the edges that is exposed to the air, and then we will make the element class flow boundary, and we need to make a new material, and we call it the convection, and it will be a heat flow boundary. And we need to enter the heat flow transfer coefficient, and we create. After creating the convection boundary condition, we also need to assign the external temperature for this convection boundary. So we call it external temperature at the thermal boundary conditions, and we add the condition case, and we select the edge and external temperature, and activate the convection boundary boundary conditions, and then we enter external temperature 15 Celsius degree. We click create. And because we are doing a transient time heat flow analysis, we need to give this boundary condition a time factor so that it will take into account. So here we set from time 0 to the end of the simulation 60-day factor 1, so which means they are constant and apply to the simulation. So after the convection boundary condition is done, we need to give the model an initial temperature. If you don't give the initial temperature to the geometry, they will end up having 0 Celsius degree at the beginning of the simulation. So we have to define the initial temperature here. We add a new initial temperature case, and we select shape, these two wall and slab, and we will use the temperature field and input the initial temperature as 20 Celsius degree. And we click create. Then the model will have the initial temperature. And the next thing to do is to assign the mesh resolution here. So in this case, we will give the slab concrete a slightly less mesh size, 0.3 meter, and we give the wall a little bit refined mesh, which is 0.1 meter for the element size. And then we click generate mesh. Then you can see that the mesh are generated for the concrete and also for the cooling pipe. Next thing to do is to set up the analysis. First, we will create a new analysis. We rename it heat analysis, and we right click at command transient heat transfer, and then we will need to set up the, for example, the initial condition first. We select the initial condition we just set, and we need to activate the nonlinear analysis so that the heat of hydration is taken into account. And please note that initial degree of reaction should be a small number, at least to require a very small number to begin the process of heat of hydration. So in this case, we just keep it unchanged, and then we click close. And the next thing is to assign the time step of the simulation. So we use the one that is provided by tutorial, and we paste it here. Then you can see that the syntax is the outside of the parenthesis is the time step, and inside the parenthesis is the number of steps. So for example, here is a 0.2 days for 10 steps, and then 0.5 days for 10 step, etc. And we click close. And we will also need to check the analysis output. So in this case, we will just use the default or primaries output, and then the analysis setup is done. So in the result, first we will check the degree of reaction. So in degree of reaction, we need to, in order to check, to fix the color scale between different time steps, we will need to fix, for example, the minimum of this value is 0 and the maximum is 1. So 0 means beginning of the hydration process, and 1 is completion of this process. So you can see that the heat of hydration, the degree of reaction, is increased with the time, and you can also see that the location, the concrete, where the concrete is next to the cooling pipe, the degrees of reaction is lower compared with what you saw in the top of the concrete wall, which is without any is far away from the cooling pipe. And you can also see the temperature result of the whole model. So we need to adjust the temperature range from 10 degree to 45 degree. And from the beginning of the simulation, you can see it the temperature of the whole model, and it changed with time. The location where there is cooling pipes is lower than the temperature, and the temperature at the top of the wall is much higher. If you go to the end, that the total temperature of the whole model is around the temperature of the cooling pipe. And you can also see the equivalent age, and we need to reset it from 0 to 35 in the unit of days. So you can see that at the beginning of this, the result is showing the age is increasing, and also you can see similar effect near for the location near the cooling pipe, and you can see that the top of the concrete wall has much higher equivalent age compared with the rest of the structure. And you can also see the internal temperature of the cooling pipe. At the beginning of the simulation, you can see that the temperature at the influx is much lower at the initial temperature compared with the outflux, which is much higher. And as time goes through, you can see the outflux temperatures is also dropping, and then in the end the outflux also having the same temperature as the influx, which is the 10 degree that we assign. If you're interested in checking the tutorial yourself, you can go to the Diana website tutorial, and find, for example, apply the filter transient heat flow analysis, then you can find the model that I introduced here today, and you can also find the Python script in this folder inside your Diana folder. Thank you very much for your attention.